Hi, everybody. Welcome to lecture number 10 for Physics 151. This lecture is going to cover the addition of velocities or relative velocities, and I'll start with some one-dimensional examples and then move into two-dimensional examples. These are located in two different sections of our textbook, so at the end of chapter 2 and at the end of chapter 3. Then the second half of this lecture will cover two-dimensional kinematics, specifically the same formulas we've been using already for displacement, velocity, and acceleration, only generalized to more than one dimension. All the problems we've been doing up until this point are one-dimensional. What we cover today is going to carry over into the next lecture, lecture number 11, on projectile motion. The related materials are tutorial 10, which I'll be doing a few of the examples from during this lecture, and the solutions are available for you to try the other ones as well. And then whenever you're comfortable, pause the lecture, stop using the tutorial problems, and then do the 4-credit problems that are in Mastering Physics for Online Homework 10. The first half of Online Homework 10 relates to this relative velocity portion, and the second half of Online Homework 10 relates to two-dimensional kinematics. So let's start by talking about relative velocity. Okay, what is this context in which we might need to add velocity vectors together? Well, first of all, let's define a very physicsy term, which is frame of reference. Okay, a reference frame or frame of reference is the sort of surroundings around an observer that appear to be sort of at rest with respect to that observer. So for example, if you're sitting in a room or if you're standing in a physics lab, then we often talk about the lab frame of reference. That is what appears to be stationary with respect to you. Okay, so if you're standing on the ground outside of a train, like in this little cartoon right here, then you are in the ground's frame of reference if you're stationary with respect to the ground, because the ground looks like it's motionless with respect to you. But if you're sitting on the train, then you are in the train's frame of reference. The train is stationary with respect to you. Notice how different frames of reference can move with respect to each other. So if the train is moving forward at some velocity, this is the velocity of the train with respect to the ground, or the train relative to the ground. That's what this little slash is used for in our textbook. Then what that means is a third object, like this person here, can appear to have two different velocities to observers observing from the two different frames of reference. So to other observers on board the train, this woman might appear to have one velocity, specifically the velocity of the woman with respect to the train. But for observers who are standing at rest on the ground outside, she will appear to have a different velocity. And that would be the velocity of the woman with respect to the ground. Which is correct? What is the woman's true velocity? Well, the answer is they're both correct at the same time. The woman has both velocities at the same time. She has one velocity with respect to the train's frame of reference and at the same time, a different velocity with respect to the ground's frame of reference. And those are both true simultaneously. We call this relativity. Okay. In other words, there is no absolute velocity for the woman. She has relative velocities depending on the reference frame of the observer. This theme is going to come back again in Physics 152 when we talk about special relativity, which was one of one of the things that Einstein figured out in 1905. And specifically, his theory of special relativity deals with what happens when you travel very fast, close to the speed of light. However, at low speeds like we have right now, we have what's also known as Galilean relativity. And in order for us to convert the velocity of an object with respect to different reference frames, all we have to do is simply add velocity vectors together. So if we want to find the velocity of the woman with respect to the ground, right, or you can say relative to the ground. So WRT just means with respect to, right, although that could mean relative to. You could just substitute relative to as well. We need to find the velocity of the woman with respect to the train, which we know that's given to us, and then add that velocity vector to the velocity of the train with respect to the ground. And what we'll wind up with is the velocity of the woman with respect to the ground. Our textbook uses a nice sort of compact notation for this. And the convenient thing about this is these are little fractions. And if you say, okay, this fraction times that fraction, then the train cancels out and you're left with woman with respect to ground. So that's one. You can have a third or a fourth or a fifth velocity vector here, and then you can use this little shorthand to make sure that they're canceling out correctly, and you're left with the the velocity of the object with respect to the reference frame that you want. So that's kind of convenient. What if, we know the velocity of, let's say, the train with respect to the ground, but what we really want in some future problem is the velocity of the ground with respect to the train? Well, if you want to just reverse those two frames, simply multiply that velocity by -1. And that just reverses the two frames. So what do I mean by that? Suppose the train is moving forward at 10 meters per second with respect to the ground. Well, to an observer on the ground, that's what they see. They see the train having a velocity of positive 10 meters per second in the positive x direction. However, what does an observer on the train see the ground doing? An observer on the train would see the ground moving backward in the negative x direction at 10 meters per second at the same time. So you can see, therefore, that the velocity of the ground with respect to an observer on the train is just the negative of the velocity of the train with respect to an observer on the ground. Okay, so if you ever need to reverse those two frames that are, or the object and frame or whatever that are in the subscript here, just multiply by -1. Okay, we're going to start with one-dimensional examples where the motion of the woman and the motion of the train are both in the same, along the same axis. So they might be in the same direction or they might be in exactly opposite directions, but everything is just along the same single axis. So that would be a one-dimensional problem. So we'll start with a one-dimensional case. However, I want to emphasize that this simple Galilean relativity vector addition here also applies to 2 or 3 dimensions as well. So we'll do two-dimensional examples next. All right, so let's take a look at the example on the tutorial sheet. So suppose that you have a motorboat and it's pointed due west, and it is in a river that also flows westward. So the river has a current, and then the motorboat itself has a motor. So we have two velocities here. We start off with the velocity, or you're given the velocity of the boat's motor and its ability to propel the boat forward through still water. Okay, so what that means is we could think of the boat here as having a velocity vector. So here's our little boat. And we could think of it as having a velocity vector through still water. And I'll call that V sub m for motor. Okay, you're welcome to just choose whatever subscripts you want. I don't want to use B for boat because everything that we're talking about is the motion of the boat. So I'll just say this is the velocity that the boat would have through still water. I'm going to drop the sig figs for the moment just for simplicity. Okay, and then at the same time there is a current. Okay, so the current is due west at a constant 1 meter per second. Oh, I'm sorry. I made a mistake. I drew the velocity of the boat east. Okay, so let me fix that right now. So first of all, I should have started off with my axes here. Okay, and then if I had been a little more careful, okay, let me erase this. And I'll redraw the boat's velocity. Okay, so the boat is actually pointed west. And so if the river weren't moving at all, the boat would have a velocity like this, 3 meters per second due west. And then the river itself, which I could call V sub R for river or V sub W for water, I'll call V sub C for current. Okay, the current is flowing 1 meter per second due west as well. So, or to use the notation that our book is using, you know what? Let's do that. This is the velocity of the boat with respect to the water, and then the current is the velocity of the water with respect to the shore. Okay, so B is boat, W is water, and S in this case is shore. And what we really want to find is what is the velocity of the boat with respect to the shore. Okay. So we know from Galilean relativity that we need to add the two vectors together. So the way I do vector addition is, well, here, let me write this out as a vector equation. The velocity of the boat with respect to the water plus the velocity of the water with respect to the shore, okay? Now, if we use our little mnemonic here, we see that we're going to wind up with the velocity of the boat with respect to the shore, which is what we want. Okay, so now I'm going to sketch the vector addition using our graphical notation. Okay, so first I have the velocity of the boat with respect to the water. That's 3 meters per second to the west. So this is going to look exactly like the vectors above, only now I'm going to place some tip to tail. Now I'm going to add at the tip of that the velocity of the water with respect to the shore, which is another 1 meter per second. Okay, and then I can draw the sum. And I'll just change color here for the sum. The vector sum is the vector that goes from the start of the first vector to the end of the last vector, like this. So this is the velocity of the boat with respect to the shore. Now, this is really the triangle method, only this is a triangle that's squashed flat because it's just one dimensional. So there's no height to our triangle. So I can just by inspection, just meaning this is simple enough that I can figure out the vector sum just by looking at it. And I can see that the vector sum for the velocity of the boat with respect to the shore has a magnitude of 4 meters per second, and the direction is due west. Okay, so I'll just do that by inspection. Now, in the second part of the problem, or I'm going to jump to part C, and in part C, it just says that the velocity of the boat turns around, so now the boat's velocity is due east. Okay, but the river is still the same. The river is still flowing due west with the same current of 1 meter per second. So now we have the boat facing due east. So the velocity of the boat with respect to the water. And the motor has one speed only. This is the velocity of the water with respect to the shore, 1 meter per second. Okay. And once again, Galilean relativity says that the velocity of the boat with respect to any observer standing at rest on the shore is equal to the boat with respect to the water vector plus, these are vectors, plus the velocity of the water with respect to the shore. That's the current. Okay, so let's draw the vector addition. So whenever things are simple and it's possible, it's always nice to draw the vector addition so we can see it conceptually and graphically. Here we go. Here's the velocity of the boat with respect to the water, 3 meters per second. And now, going back in the other direction, we have the velocity of the water with respect to the shore, 1 meter per second. So if I draw the sum now, again, the sum is the vector that goes from the start of the first vector to the tip of the last vector. So that's this vector right here. That's the total, or net, or resultant, or sum. And that's the velocity of the boat with respect to the shore. And by inspection, we can see that that is simply equal to a magnitude of 2 meters per second due east. Okay, and again, we're using formally, we're doing the triangle method, we're doing geometry here, but it's just such simple geometry. It's a triangle that's been squashed flat. So we can sort of say, well, all right, I can just see it by inspection. I can see the answer. Okay. All right, let's go on to, let's briefly talk about the theory, look at some examples of two-dimensional velocity addition. And that is, what if you have an example where the two or more of the velocities that you want to add are not, the two or more velocities that we want to add, okay, like in this case of finding the relative velocity again, are not all in one dimension. They do not all lie along just one axis, just the x or just the y-axis. In this case, for example, suppose that the woman on the train is walking in this direction, which is perpendicular to the motion of the train. Well, in that case, we could ask the question, what's the velocity of the woman with respect to the ground outside? Well, this equation, this vector equation here, is unchanged. This Galilean relativity vector equation is exactly the same for 2 dimensions as it would be for 1 dimension. The only thing that is now different is now when we put the velocity of the woman with respect to the train and add that to the end of the velocity of the train with respect to the ground outside, now we see that that forms a triangle. And then the sum of those two velocities I've drawn here in blue is from the start of the first vector to the end of the last vector. Okay, and that's the velocity of the woman with respect to the ground outside. And you can see that in this case, first of all, 3 meters per second plus 1 meter per second do not add up to 4. In this case, they add up to 3.2 because of Pythagorean theorem, first. And second, the direction is not exactly along the motion of the train either. To an observer at rest outside with respect to the ground, the woman's velocity is at some sort of an angle with respect to the motion of the train. In fact, it's 18 degrees. It's 18 degrees off from the direction of the motion of the train. This example is encountered a lot when we have boats crossing rivers that are when the boat is trying to cross a river that has a cross current, or we have an airplane flying in a crosswind. So, for example, suppose this airplane here has its nose pointed due north. So, if the air were perfectly still, the airplane would fly due north, and it would do so at 240 kilometers per hour. So it flies, the velocity of the plane with respect to the air is 240 kilometers per hour. However, the air itself is moving with respect to the Earth with this 100 kilometer per second crosswind. And this particular example here, it's due east. So what is the net motion of the plane with respect to the Earth below? And by the way, this is all pilots know that as the ground speed, right? They call it ground speed, but it's actually a vector. It both has a speed, but also a direction. So what will be the overall net motion of the airplane with respect to the Earth below? And the answer is, well, it'll have this magnitude, which is some sort of Pythagorean combination of the velocity of the plane with respect to still air and the velocity of the air with respect to the Earth below. And then the direction also will be pushed off to the side. It'll be pushed to the east by the crosswind. So this will be some net direction, alpha degrees to the east of north. If the pilot really wanted to go due north, if the destination that the pilot was trying to get to is due north of their starting location, then what they should do is they should point the nose of their aircraft into the wind slightly, okay? And the amount that you need to point it into the wind, you can calculate from this vector sum now. So suppose that this aircraft engine has one speed only, right? This aircraft, when the propeller's on, only travels at one speed, which is 240 kilometers per hour with respect to still air. So that won't change. So you can see that the length of this velocity vector here, which is the airspeed of the aircraft, right? The velocity of the aircraft with respect to still air is still the same length. It's 240 kilometers per hour. The only difference is that we've tilted it beta degrees to the west of north because this smart pilot here, they know that they need to fly into the crosswind a little bit in order to have a little bit of their aircraft's engine cancel out the wind, right? Have their motor cancel out the wind. Then what will happen is the crosswind will blow them back on course. So here we have the exact same crosswind, 100 kilometers per hour, pointed due east. So we add that velocity vector to the airspeed velocity vector of the aircraft. And what happens? This aircraft gets blown back on course, which is due north. Notice that this velocity vector here is a little shorter than this one over here, right? So the ground speed of the aircraft in this case is slower than whatever it would have been in the first situation, right? Notice if you stand back and look at these two triangles, these are not the same triangles, right? 240 kilometers per hour is one of the legs of the first triangle, but 240 is the hypotenuse of the other triangle. So these are not the same triangle, and therefore this angle alpha is not the same as the angle beta, although they are kind of close, okay? So then the smaller the crosswind is, the weaker the crosswind is, the closer these two angles will be. But they are not the same angle. They are different. These are two different triangles here. Okay, so here we have an uncorrected aircraft just being blown downwind by the crosswind. And here we have an aircraft whose route is corrected by a smart pilot who took physics and knows how to calculate, using the help of their avionics, knows how to calculate a new bearing, a new heading to counteract the crosswind. Okay, so we're going to do these two examples right now with a boat trying to cross at right angles to a flowing river. And this is also from our tutorial number 10. So this is problem number 2. And we're going to do 2A and 2C. And again, these are the examples. These are very similar to those two cartoons that we just saw with the aircraft. So I'm going to change the view now, so that way you can see me solve these with pencil and paper. Okay, so here I have, and just because this is going to be a little too complicated and intricate for us to just draw with the stylus. The stylus does not give me much resolution. Okay. All right, so in the case of 2A, what we have is we have a motorboat's bow that's pointed due north as it tries to motor across a river. And this is what the speed of the motor would be in still water. So the same as in the one-dimensional case that we just did. This little motorboat, if you put it in still water, would propel forward at 3 meters per second. This particular river's current is flowing due west at a constant 1 meter per second. So what we have here, if I just sort of sketch out what these two vectors look like, and by the way, we're going to skip part B for now. Okay, so if I just sketch out what these two vectors look like, we have a boat whose bow is pointed due north. And if you put it into still water, then this is the velocity of the boat with respect to the water. And this would be 3 meters per second. Again, I'm just dropping the sig figs just for speed and clarity right here. Okay? Right. And then the river itself flows due west at 1 meter per second. So the velocity of the water with respect to the shore at 1 meter per second. So now we can ask the question, all right, what is the magnitude and direction of the boat's net velocity relative to the shore? Okay, so what is the net velocity of the boat with respect to objects on the shore? Well, we know that Galilean relativity tells us velocity of the boat with respect to the shore is equal to the velocity of the boat with respect to the water vector plus the velocity of the water with respect to the shore vector. Okay, so this is a vector sum. And let's sketch what that vector sum is going to look like. It means just so that way I have sort of a mental idea of what we're going to be doing. So what I want to do is I want to do the vector sum of these two vectors here. So let's draw the velocity of the boat with respect to the water. Okay. I'm going to try and, I know that this is 3 meters per second long, this vector right here. And now I have the velocity of the water with respect to the shore. And I should make that 1 meter long. And then the sum is going to be from the start of the first vector to the end of the last vector, like that. So I'm going to try and make the sum here a very heavy line. Okay, so this is the total velocity of the boat with respect to the shore. All right, what else do we know about this? Oh, well, now I have a choice. How do I do a vector sum? Okay, I can either use the triangle method, which is okay if you have only two vectors, and they form a nice triangle, right? So that we'll just be using SOHCAHTOA, Pythagorean theorem, and it's pretty straightforward. Or I could use the component method at this point. And in this case, I could probably write out these two velocities pretty quickly as far as the component method, right? So either of those would work. I think what I'll do is I'll follow the triangle method right now. And to use the triangle method, what I need to do is redraw this little vector sum here just as a primitive geometric figure, and then decide what parts of that geometric figure, in this case a triangle, we want to solve for. So triangle method for vector addition. So I'm going to take this vector sum, I'm going to just recast it as a simple triangle, and I'll inventory everything I know about this simple triangle, and I'll inventory what I want, what the unknown quantities on the simple triangle are that I'm trying to solve for. Okay, so I know that this side up here has a length of 1 meter per second. Notice I'm saying length, geometric length for the vector, but it's not actually physically a length, right? This is a, is that sharp? Good. Okay, this is a, okay. These are velocities, right? They're not distances, just to be clear. And then this is the velocity of the boat with respect to the water. And this side has a length of 3 meters per second. And I know that's a right triangle, that's a right angle there, because this is due west and that is due north. Okay. So what do I want to find? I want to find this hypotenuse side right here, which is the velocity of the boat with respect to the shore. I also want to find the angle of the boat's motion, right? If I go back to my vector sum drawing over here, I want to find out this angle here, which is a number of degrees to the west of north the boat has been pushed by the cross current. So let's call this alpha. All right. So I know two sides and an angle in this triangle. So I should be able to solve for any of the other parts of the triangle that I want. So to get the magnitude, I'm going to use the Pythagorean theorem. And again, these have 3 sig figs on them. But just to save me space for speed, I'm just dropping the sig figs for the moment. Okay. So I asked my calculator what it is, and it says 3.162, et cetera, meters per second. Let's round that off to 3 sig figs. All right, so that was the magnitude. Let's get the direction. Let's get the angle alpha. Okay. Well, it really is sort of the angle of the V with respect to shore. Bearing in mind it's not the trig angle, it's this angle of degrees west of north. Well, all right. Now I know everything about this triangle. I know all the sides of the triangle. So I have a lot of options available to me. I could solve for angle alpha by taking the inverse sine of opposite over hypotenuse. I could take the inverse cosine of adjacent over hypotenuse. Or I could take the inverse tangent of opposite over adjacent. Any of those would get me to the answer. So I'm just going to choose. I'm just going to pick one. I'll pick tangent. So we know that tangent of alpha is equal to opposite over adjacent. So therefore, I can solve for alpha by taking the inverse tangent of those two values. That's the inverse tangent of 1 meter per second over 3 meters per second. And when I ask and notice the units cancel out, which is good. You want to feed inverse trig functions dimensionless values. And when I ask my calculator what the answer is for inverse tangent of 1/3, I get 18.4 degrees. And there's another answer to the inverse tangent that's 180 degrees away from this, but I'm not even going to bother to calculate what that is because I can see by inspection. I mean, I know alpha needs to be an acute angle, it needs to be something small, less than 90 degrees. So that's the answer. So therefore, to write out the whole vector, therefore the velocity of the boat with respect to the shore, if I'm going to write out the entire vector, it's equal to a magnitude, 3.16 meters per second, at a direction of 18.4 degrees west of north, right? Degrees to the west of north. All right, so that's the full vector, magnitude and direction. Right, and those are the two parts of question 2A. Now, question 2C, Let me zoom out just one notch here. Question 2C is going to say, all right, suppose that the boat pilot gets smart and he says, all right, I want to go straight across the river instead of drifting. See, what's happening right now is the little boat is keeping its bow always pointed due north, but he's being pushed to the west of north by this current. So suppose he says, I want to go due north. My destination is due north of me. So what I'm going to do is I'm going to point the bow of my boat into the current, right? I'm going to point it up current by a certain amount, and I want to calculate how much. Okay, and that way, as he motors across the stream, his resulting motion will be pushed back on course due north by the current, by the motion of the current. So what we're going to do is draw a new vector situation here. Okay. Okay. So we have the magnitude of the boat's velocity doesn't change, but now the boat is going to be pointed at some other direction, at some direction east of north. So we're going to have, so here's the boat again. And let me zoom in. Okay. So again, here's the velocity of the boat with respect to the water. It's still 3 meters per second. And it now is tilted east of north by some amount. And we're going to calculate what that is once we do the vector sum. The current, the river has not changed at all. Okay. So we have the velocity of the, here, I'm just going to save space a little bit on the page. So I'm just going to put it up here. We have the velocity of the water with respect to the shore. That's the current. And that's still 1 meters per second due west. All right. All right, so now what does our vector sum look like? Right. The velocity of the boat with respect to the shore is going to be the sum of those two vectors. Velocity of the boat with respect to the water plus the velocity of the water with respect to the shore. And that will give me the boat with respect to the shore. So let's add, okay, boat with respect to water, tip to tail. So now we're doing this graphical representation of the vector addition. Okay. And how do I know how far to draw that? Well, if I were measuring this with a ruler, I need to make sure these in a ratio of 3 to 1. But I also know what the outcome is supposed to be. I know the outcome is supposed to be that the net velocity of this, of both of these two together, is supposed to be due north. Right? So I know, by the way, so going from the start of the first vector to the tip of the last vector, I know that the net velocity of the boat with respect to the shore needs to be due north. Right? That's supposed to be the case. Right? So that's actually our sum. That is now the vector sum of the two velocities. Notice it's not the hypotenuse that's the sum anymore. It's this leg of the triangle. That's one, that is the sum. All right. So let's, again, we could use a component method, but let's use a triangle method instead. I think, in fact, in this case, the triangle method is probably much simpler because the component method would involve an unknown angle right here. And that means we'll have an unknown angle beta hanging around in all of our sines and cosines. So I think the triangle method in this case is actually preferable. So I'm going to, again, extract this as just a primitive geometric figure without the heads on the vectors or anything like that. And I'm going to reproduce all the lengths and angles that I know and identify the lengths and angles that I want to find. So I know that I know the length of this side up here. I know the length of that side down there. Notice these are just magnitudes now, right? I know that this is 3 meters per second. Do I know, and this, the length of this side now is unknown, okay? That's one of the things we're going to solve for. And what else do I know? I know that, this vector up here is due west, that one's due north, so therefore the angle between them needs to be exactly a right angle, okay? If I want to know, and as the boat captain, we want to know, all right, what's the angle that we should point the bow of our boat into the oncoming current, right? So what's that angle that I want to adjust by to counteract for the oncoming current? All right. So triangle method. All right. So I know two sides and an angle on this triangle. So therefore, I should be able to solve for any of the other sides and angles. right? Um, the first question here asks for the direction of the bow of the boat. So let's go ahead and use and find the direction first. Okay, so the direction of the bow of the boat. So I'm sorry, I made a mistake here. This is the boat with respect to the water. Okay. 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 So in this case, my options are more limited because the adjacent side is still unknown, but I know the opposite side and the hypotenuse of this right triangle. So I think that means I need to go with sine, right? Sine of beta is going to be equal to opposite over hypotenuse. So I can find what beta is with the inverse sine. Again, these have 3 sig figs on them. I'm just saving space. So I asked my calculator, what's the inverse sine of 1/3? And it tells me that it is not 18.4 in this case. It is 19.5. So it's close. It's similar. It's not, wildly different, but it is not exactly the same as it was in part A. Right? Because it shouldn't be. These are not the same triangle. Okay. And then so this is 19. So just to be clear, that's 19.5 degrees east of north. And that's actually sort of a separate final answer, right? That's for this vector over here. Let me zoom out a little bit. Okay, that's for this vector right here, right? The velocity of the boat with respect to the water. Now I'm going to find the magnitude of the velocity of the boat with respect to the shore. Okay. Okay, so now we can use the Pythagorean theorem. And the Pythagorean theorem says, all right, this sum of these two legs squared gives us the hypotenuse. So here's what I want to find. This is 1, and that one's 3. And again, these all have 3 sig figs. So then I solve for the velocity of the boat with respect to the shore. So that's the total or net velocity of the boat. Right. And that turns out in this case to be 2.828, etc. If I say, oh, it's about a 3 sig fig, it's about 3 sig fig problems. This is 1.00, 3.00. So that's about 2.83 meters per second. Right. And if I wanted to know the direction, then, well, we already know, we're told in the problem that the direction of the boat's net velocity is due north. All right. Okay, so at this point, we're going to return to the slides and talk about some theory for two-dimensional kinematics. And what I'm going to do is I'm going to stop the lecture right here. What I actually recommend is before we go on to 2D kinematics, if you like, you can pause the lecture and go to the online homework and do the first half of the online homework in Mastering Physics, which are about just adding in relative velocities. So just one-dimensional, two-dimensional addition of velocities, and do some of those problems now. I'll stop the lecture at this point and continue as part 2 of lecture 10.